Only 12 questions, all multiple choice. So normally if I have 12 questions of multiple choice, I give 2 minutes per question. That's average, so 24 minutes would be the normal time. But normally I don't like to rush people, which is good and bad. I guess good because you can go back and check your answers. Bad because it's not the norm. UCLA, it's like you're going to be rushed. Everywhere you're going to be rushed. So anyway, so I'm going to give more than 40 minutes for this, you know. So some people will finish early, and some people will just take a more relaxed approach, leisurely approach. You can take as much time as you want. Even if you go overtime a bit, it's all right. I mean, my office half hour bleeds over, so I'll just stay. Anyway.
At the beginning of the period or the end?
At the end. So once you're done with the test, you're free to leave. We're not going to do anything else after that. All right, Gavin, what was your question?
So we're free to leave after.
Yeah. We're going to have lab today. So we'll have lab for the first part of class and then the test. So I think most people finished the lab without a problem and had plenty of time for the test. The lab isn't so long today.
The stuff we need to write down lab posted on campus the day before, or
It's on the syllabus. So you go, and then I gave a zip file with all the labs in it. And so you just skim through the lab.
okay.
Some people prepared their lab notebook. They wrote everything in there, but you don't have to.
I mean, are you just interested in the data and answer the questions, or?
The pre-lab you don't have to do unless I make an announcement. And so skip the pre-lab. Today's lab, I'm interested in data. Normally when we have lab, you come in and a day of lab is just data collection. And then after you collect all your data, then you'll have data analysis and report writing. So that's how it's normally going to work. Today we're doing the Le Chatelier's lab. Let's see if I can get this. Le Chatelier's principle. So let's look at an example of Le Chatelier's principle. So if I have some silver chloride solid, is it soluble or insoluble? Silver chloride solid. It's insoluble, but that doesn't mean it's infinitely insoluble. In other words, a tiny, tiny bit will dissolve in water to form silver ions and chloride ions. In other words, it's not absolutely insoluble. There's a cutoff. For something to be insoluble, all it means is that less than 0.1 moles will dissolve in the liter. It's actually a lot less for silver chloride. It's like a micromole will dissolve. But that micromole that dissolves will give us an equilibrium like this. Silver chloride is insoluble, so the favored direction is to the left. But a tiny bit will dissolve and will create a dynamic equilibrium. The dynamic equilibrium is going to be between the solid and its saturated solution. Once the solution has been saturated with silver ions and chloride ions, then there's no more net change, and we've reached this state of dynamic equilibrium. But the dynamic part of the equilibrium is that the crystals continue to dissolve and the ions continue to precipitate. So we're just going in circles here. We're going in circles here, but nothing overall is changing. I have different sized arrows just to indicate which is the favored direction, reverse. But in reality, both directions are equal in terms of rate. That is, the rate of dissolving is equal to the rate of precipitation. Another word for dissolving is dissolution. But this is our dynamic equilibrium. And so we do different things for this. Let's say I want to precipitate out as much silver ion as possible. Is there a way to get more silver out in the solid form than in the aqueous form? One way we do this is by adding more chloride. If we add more chloride, we can shift this equilibrium to the left, and that will create more precipitate. Correct? And so what we do is we just say increase the chloride. There are different ways of increasing chloride. We could add like sodium chloride or HCl or some other chloride source. But ultimately what we want to do is we want to increase the chloride concentration, and that's going to shift it to the left, and then it favors precipitation. Uh-huh.
What makes the increase in chloride be sort of the thing that will give us more precipitate than silver chloride instead of adding more silver?
Well, adding more silver will do too. That's another option. We could add more silver ion, and then we'll generate more precipitate. So either chloride or silver. That's fine. I'll just write that here. How about the other option is, we can increase the products. We could also decrease the reactants here. But this one's very tricky because, the equilibrium law needs to be in terms of what? The equilibrium law, is it in terms of concentration? Not really. It's really supposed to be in terms of Well, we could do it in terms of concentration. So let's say you had 1 gallon of milk. If you drink half of it, so now you only have a half gallon. So you started off with 1 gallon, now you have a half gallon. Is it going to be half as concentrated? In other words, let's say you had 1 pound of pure gold and now you have a half pound of pure gold. Is it still pure? And so concentration, well, it's pure. So if I have, let's say, 1 gram of pure silver chloride and I took half of it away, now I have a half gram of pure silver chloride. Is it less pure than it was before? No. And so what we say is the concentration doesn't change. It's still pure, 100%. It's kind of weird to think about concentrations of things that aren't solutions. Do you know the concentration of pure water? If you had 1 liter of water, 1 liter of water is 5,000. Wait, no. 1 liter of water is 1,000 grams. A mole of water is 18 grams. And so if you're to calculate it, there's 55.5 moles in a liter. And therefore the molarity of pure water is 55.5 molar. So if you got a glass of water and that's 55.5 molar and you drank half the water, is it now half as concentrated or is it still 55.5? It's still 55.5. And so in other words, the equilibrium law should be in terms of activities, not of concentrations. But regardless, the activity of pure solids is what? The activity of a pure solid is 1. And so it doesn't change. And so in other words, if we remove or if we add silver chloride, it doesn't change the equilibrium. I just need to have some silver chloride in there. And that's it. So, what favors dissolution? Okay, so this favors precipitation. How can I favor dissolution?
Decrease the amount of the ions.
Yeah, well, what if I add just DI water? If I add DI water to this, does it decrease the amount By adding water? And no, the amounts stay the same, but what I do by adding DI water to this is I decrease the concentration. And so I could just add water. And if I add more water, then I'm going to be able to dissolve more silver chloride. And so I can increase the water, the amount of water. That's going to decrease the concentration of silver ions and chloride ions, which is going to shift it to the right. And it favors dissolution. By adding more water, is that going to change the concentration of solid silver chloride? By adding more water? No, because the solid itself, even though you're going to have a lot of water in there, the solid itself is still pure. And so that doesn't change the concentration. So adding water only impacts one side. Sometimes adding water impacts both sides equally. And so there are cases where adding the water has an equal effect on the reactants and the products, therefore nothing happens. It doesn't shift it one way or the other in Le Chatelier's terms. But adding water will decrease the concentration of the products, which favors dissolution. Okay, the other option is I could remove. Let's say I don't want to add any more water. Is there a way I can remove these ions out of here? I'm sorry? Like a filter? Are there filters? Yeah, there are some filters that do this, but they aren't like paper filters. Like our deionized water goes through a filtration system where it removes all the ions.
Don't you like put them in a centrifuge and make it easier for you to pour it out? Precipitated?
Yeah, but the problem is these are like permanently suspended. If it were like a heterogeneous mixture where you have some like sludge in there or some solid, then it would compact to the bottom. But there's no way you can centrifuge the silver and chloride ions.
Oh,
They're
wait.
just too light.
I think I forgot to add the fact that like you want to add something that causes it to precipitate and then make centrifuge so it's the solid.
Yeah, we have a precipitate over here. Like what would you give as an example as a precipitate? What would you add?
You know, I don't know actually because AgCl is already pretty insoluble, so.
AgCl is pretty insoluble. So what we could do is we could set up a competition. So this favors dilution. So this would be an example here. This is an example of Le Chatelier's. Another example would be to have a competing ion. And so we can do some kind of chemical removal of this. This would be physical. We just add more chloride in there, and then we get that chemical reaction here. And so let's take a look at using some of the chemistry of this. To determine. So what we can do is we can set up a competition for silver. So if we look at Ag plus Cl minus, this goes to AgCl solid. Oops. That's one way. Or I'll just write it back. You know, it doesn't matter which direction we write it. We can either think in terms of left or right. Ag solid goes to Ag plus Cl minus. So I could write it either as the precipitation reaction on the top or the dissolution, but really both are the same because when I look at these, they can go either direction. These are reversible reactions. So I can just write it either way is fine. Now, when I look at the silver ions are reacting with chloride, but what if I put another species? Do you know what prefers silver more than chloride? Lead 2 plus? Okay, maybe lead 2 plus would remove the chloride, but lead 2 plus isn't as good.
Sorry.
No, actually sulfide would be good. Sulfide would be good, or bromide. Let's do this. What I'm going to do is I'm going to set up a competition. I'm going to put in some bromide in here, and I'm going to have bromide versus chloride. Who will win? All right, now what we did was both are insoluble. So it's going to be a tie because silver bromide and silver chloride are both insoluble solids, right? But our solubility rules have just this cutoff, which is 0.1 moles per liter. But there are two solubilities that we deal with. One solubility is the qualitative one, 0.1. If it's less than 0.1 moles of solute dissolving, we call it insoluble. If it's more than 0.1 moles of solute dissolving, we call it soluble. If it's around 0.1 moles, we'll call it slightly soluble. That's qualitative. We also have a quantitative solubility. The quantitative solubility is how much will dissolve in a liter, or how much will dissolve in 100 milliliters. So for example, sodium chloride is not infinitely soluble. When we look at its actual solubility, it's only 36 grams. We can dissolve 36 grams of sodium chloride in 100 milliliters. That's the max. And so the other way of looking at solubility is the maximum that will dissolve. When we compare silver chloride and silver bromide has a lower solubility. How do I compare them? I compare them by looking them up in a book, a book of data, or Wikipedia. Wikipedia has this data too. The CRC, Chemical Rubber Company Handbook of Chemistry and Physics, has it. And so I compare the two, the actual solubilities, and see which one is less soluble. The one that's less soluble is the one that's more stable and more favored. And so what I could do is I could set up a competition, and if bromide's more favorable, precipitate, then that's going to win. And so eventually I'm going to convert all my silver chloride into silver bromide. That's one. And so I can have it competing. Or on the other hand, I could try, chloride, silver, rather than silver, I might put in lead 2. But lead 2 is going to lose because the solubility is really high on that. But I could try other things, or rather than bromide, I could try sulfide. Sulfide is much more stable. And so what this is going to do is going to remove the silver ion here and dissolve the silver chloride. Eventually I'm going to dissolve all the silver chloride, and I'm only going to be left with silver bromide. And so this is taking advantage of Le Chatelier's to do that. And what I'm doing is I'm setting up what type of reaction is this? Silver and bromide. Metathesis. So I'm looking at which one's a more favorable metathesis, which one forms a more stable ion combination. And the way I do that is I don't do it theoretically. You could try to do it theoretically, because if you do it theoretically, I would have predicted silver chloride to be more stable. Do you know why I would have predicted silver chloride to be more stable? I would have thought silver chloride is more stable because of the size. Silver ions like this, and then chloride is like this. Okay, so silver ions about the same size here, but is bromide bigger than silver or smaller than chloride? Bigger. So which one is going to be a stronger ionic bond? Silver chloride is going to be a stronger ionic bond, and that has to do with charge density. When we look at the charge density here, it's concentrated. Whereas over here, the charge density is less concentrated. And so we're going to get a stronger bond. But why is it that silver bromide is? Why is it? Is because this is purely ionic, and this is what, this is our first approximation. We just treat it as purely ionic, but in reality there's some covalent interaction. And if there's covalent interaction, we have to look at how the orbitals combine to form molecular orbitals. If we have to look at how the orbitals combine to form molecular orbitals, then we need, what was that theory? Molecular orbital theory, and we need linear combinations of atomic orbitals. And if you recall, the best linear combinations of atomic orbitals come when the orbitals are,
Straight, like,
well, yeah, you want them straight, but you also want them a different type. Like soft. Soft prefers hard, or soft prefers soft? Soft prefers soft. And so silver is somewhat soft, and then bromide's softer than chloride. Chloride's harder. Bromide's softer, more polarizable. And so there are other interactions there beyond the straight electrostatic. But based on straight electrostatic, this is going to be a stronger electrical attraction than this, Coulomb's law. Coulomb's law says that the force of attraction is going to depend on the charges. Well, the charges are the same, divided by the distance between the center of charges. So the distance here is shorter, the distance here is longer between the centers of the ions. And so Coulomb's law says silver chloride's stronger. However, when we factor in MO theory and other things, then silver bromide's stronger, the stronger bond, but it's not so easy because MO theory is more complicated. Uh-huh.
So would you say that there's two types of bonds happening?
Mm-hmm. Right. Yeah. It's just like when we say something's soluble and something's insoluble. That's our black and white picture of it. But what we have is you might say it's either ionic or it's covalent. Well, it might not be at the extremes. It's most likely in between, somewhere in between. We need to know what the extremes are, so that's why we do the oxidation state and formal charge to see where the extremes lie, and then we figure out it's somewhere in between, which gives us the delta pluses and the delta minuses. This is a metathesis. What other types of reactions can you have with silver ion? So metathesis, it's either going to react with, it's going to react with a lot of stuff. Chlorides, bromides, it could react with what? Sulfate, hydroxide, chromate, carbonate, phosphate, sulfide, all those we could do metathesis reaction with. Okay, give me another type of reaction. So this is metathesis. Just figure out what precipitates out with silver ions or chloride or both. And set up a competition this way. That's going to shift this to the right by removing silver ion. What is there another reaction that can remove silver ion from there? Redox. Okay. One thing is you could dip your finger in this solution. If you dip your finger in this solution and then you remove your finger, it's going to be completely discolored. You know what color? Yeah, because you're going to have tiny crystals of silver metal. Tiny crystals of silver metal are black in appearance, and that's one way. So if you stick your finger in there, your finger is going to be the reducing agent, your skin, and the oxidizing agent will be the silver ion. But don't do that, obviously. That's, we can use some other, because silver is considered a heavy metal. Heavy metals are going to have a significant covalent interaction. And so that's another way you can remember. And you don't want heavy metal poisoning. That's with silver ion. Silver metal's okay. Silver metal's fairly unreactive, pretty inert.
That's the case, and why is like silver jewelry not dangerous or anything like that?
Yeah, silver, because it's hard to oxidize.
Also, doesn't it tarnish and whatnot?
Yeah, it tarnishes. So you can get heavy metal poisoning that way too. It's not as bad as, let's say, mercury, in terms of damage.
Well, doesn't mercury
Oh yeah, you can inhale it as well. But mercury salts are the really bad stuff. Unfortunately, there was a professor working with some mercury salt, and as a precaution, this professor wore 2 pairs of gloves. This is a theory, or is this a hypothesis? This is going to be a hypothesis. So this professor was wearing 2 pairs of gloves and was working alone, and apparently must have dropped 1 drop of this mercury compound on one of the gloves, and it permeated through the gloves. The gloves aren't 100% impermeable. Permeated through the gloves, and but the professor quickly pulled off the gloves and washed. This is all speculation. This is a hypothesis because they can't figure out how she died. They're trying to figure it out. Yeah. But they suspect that it was mercury poisoning that led to it. So it's a different level. Whereas mercury vapor, in this lab, there's probably mercury vapor from people who broke thermometers. Mercury vapor is bad too, but not nearly as bad as the mercury
I
ion.
think they use that anymore. Mercury thermometers.
Yeah, you wouldn't think they use them anymore, but we still have them. I don't know why. I thought we got rid of all of them.
It'd be like lead for, it's really terrible for you, but it costs money to replace it, so they don't.
Yeah, but the alcohol thermometers aren't that expensive, so I'm not sure. Maybe it's the budget, you know. Yeah, Dr. Karen Wetterham, chemistry professor at Dartmouth College, died from mercury poisoning in 1997. How did the accident happen? These are all hypotheses. Because nobody was there. There were no witnesses. And so it's not quite as when it becomes it was just 1 drop. You would think 1 drop, come on. But it's extremely toxic, this stuff. Dimethyl mercury. Dimethyl mercury is fairly nonpolar. It's wearing latex glove. Latex isn't so great. Latex works for a number of things, but for a lot of chemicals, it eventually permeates through. So if you spill some and you remove the glove quickly, yeah, okay, maybe you're safe. Probably that's what she did. But anyway, it's a toxic colorless liquid that looks like water. A drop of DMM seeped through her latex glove and onto her skin. Symptoms started gradually, like a stomach flu, but worsened over time. She was hospitalized in January 1997 and died in June 1997.
What type of gloves was she using?
Latex. Just the thin latex gloves you can get at the supermarket. But if you're working, I actually worked with dimethyl mercury. I was wearing 2 pairs of gloves and nitrile gloves. Nitrile gloves get a lot more chemical resistance. And so I didn't, when I was working with dimethyl mercury, this happened around the time I was working with dimethyl mercury. Yeah, I didn't realize, I didn't even hear about this death until much later. And so I've gotten lots of splotches of silver nitrate all over my hands. I'm still here. I haven't died yet, so I'm not worried too much about the heavy metal poisoning, although my IQ is probably going down because it apparently lowers your IQ, all this heavy metal stuff. Did I tell you about, we worked with a lot of heavy metals in my lab. We worked with a lot of thallium. So I was sharing an office, and I had my coffee mug. I think it was maybe it was even a UCSB coffee mug or something. And my office mate put their sample of thallium, some thallium salt in here. Thallium's been used for murder for many many centuries, I think, as a poison. They put their sample of thallium into my coffee mug because normally you have a holder for your tubes. These are NMR tubes. They're really thin tubes and they're really fragile. So you put them in the small beaker or holder. But there wasn't a small beaker or holder in the office, so they put it into my coffee mug. And then I was kind of pissed off because I was thinking, what are you trying to do? Kill me? I was thinking. And they said, "Oh, what's the big deal? Come on, relax. It's inside glass. There's no way it's going to get through the glass and into your coffee." But then I just thought, then I realized, they were being serious. I mean, they weren't trying to intentionally do anything bad, but it's their idea of safety and hygiene was completely different than mine. Whenever I was working with the mercury stuff or the thallium stuff, I was like really cautious, maybe like what they call those, just overly like hypochondriac type, hyperchondriac.
But you caught them, so they got that lie.
Yeah, maybe maybe they wanted the whole office themselves, rather than sharing the office. You never know. But getting back to this, yeah. So don't use your skin, don't use your eyes to do this. It takes a long time to come off, and this is a serious eye hazard. And so we're going to be working with some silver salts. And so watch out, heavy metal poisoning plus silver ions are good oxidizer. So give me a different reducer. Rather than using your eyes and your skin to reduce the silver ions to silver metal, what can you use? Give me another reducer. What? Hydroxide? Hydroxide's not a great reducer. The reason hydroxide's not a great reducer is oxygen's -2, and oxygen holds onto those electrons very tightly. It doesn't let them go. So even though oxygen has 2 electrons, it can potentially lose. Hydrogen doesn't have any electrons it can potentially lose. It holds on to them like fluoride. It just doesn't let go. It's like water. Water's not a good reducer. I wouldn't use water for this. So think of something else that's a good reducer. Lithium. Lithium is too good. Lithium's too good because water is not a very good oxidizer, nor is it a very good reducer. But water is a strong enough oxidizer to oxidize lithium metal. So if you dump lithium metal in here, the water will immediately attack it, and then the hydrogens pluck the electrons off lithium atoms and makes hydrogen gas. Hydrogen gas is explosive, so if we use lithium metal to try to do this, we're going to just end up having an explosion. Hydrogen explosions, unfortunately, you might think twice about working in a chem lab because there was a hydrogen explosion more recently than this mercury death. Let me happen to my Oh, wow. I didn't realize that it was a spark. Okay, this wasn't it. This was, let's see, 2016. There was another explosion. This person just lost their arm, but they survived. This was at University of Hawaii. This is the lab, hydrogen explosion. So you don't want something like that to happen. So you wouldn't use lithium. In fact, you wouldn't use any of the alkali metals because the alkali metals are powerful reducers. Remember, metals tend to lose electrons, so metals are good reducers. What's the strongest reducer? Well, this is kind of weird because lithium. But what's the most metallic of all these elements? Do you know which one's most metallic? Cesium, francium. These ones are very easy to lose electrons because they're very big. And being very big, they're easier. Lithium is smaller and harder to lose. So lithium doesn't react as violently. You know, it gradually builds up and then you have an explosion. Whereas cesium would automatically, immediately explode. You know. And so metals lose electrons. In fact, metals, all these are reducers. And then over here, all these are oxidizers because these nonmetals tend to gain electrons. Like fluorine gains electrons, oxygen gains electrons. And so the best oxidizer is going to be here, fluorine. The noble gases are in a category themselves. But fluorine's the most nonmetallic. It's going to gain the electrons the strongest. Non-metallic properties are more complex because there's greater variety. Metals are more simple because all they do is lose electrons to form cations. And so the most metallic, cesium, francium, the most non-metallic, fluorine. And then what happens is it gradually goes from losing electrons to some kind of middle ground where it can lose or gain to where it gains, or preferentially gains. And so give me another reducing agent that's not so dangerous. We could use hydrogen gas. Hydrogen gas is a pretty good reducer, except it's dangerous. Looking at this explosion, this one only resulted in arm loss, but there was one that resulted in a death here.
A hydrogen explosion, what caused the Hindenburg?
Yeah, right. Hindenburg. There was another death. Where was it? Oh, here. This one. This is the death. Oh, this was the death. This wasn't the death at University of Hawaii. Unfortunately, this was the death. Do you know about this one?
Is she the one that got lit in fire?
Yeah. This one happened at UCLA. It's kind of a sad story because she had just graduated with her bachelor's and was taking, I think, a gap year and then trying to go to med school after that. And so she was just working as a staff scientist there. But she didn't have that much experience working with dangerous chemicals, like these pyrophoric ones. And so,
Was it like a flammable, was her sweater like flammable?
yeah. Yeah. This is the liquid here, when it comes into contact with air, immediately bursts into a flame. So we call it pyrophoric materials. And so you can't let it contact air. You have to avoid contacting air. So what they do is they do this in sealed containers. So they have a sealed container here with no air inside. And what they have is like a bottle cap on top with a little rubber piece there, a septum, and they poke a syringe in there. And then they pump it full of nitrogen or some other inert gas, a relatively inert gas, and then they transfer liquids from one container to another. Yeah. That's the cheap way of doing it. There's a more expensive way of doing it, and that's using these glove boxes where they fill them with inert atmosphere, and then you use gloves to manipulate your stuff inside of it. But anyway, give me another reducing agent that's not as violent as lithium. Mm-hmm. Aluminum. Aluminum would work well. So we could use some aluminum here. And then what we're going to do is we're going to precipitate out silver solid, silver metal. Initially the precipitate's going to be black, and then as the crystals grow bigger and bigger, they change color to a nice silver color. But we could use aluminum. That's a pretty good reducing agent. And so this would be an example of redox. Aluminum is used a lot. In fact, I have a kit that I got. Well, it's not a kit. It's a homemade kit. I made a kit. You know, silver tarnishes. So you get that black coating on the silver, And so what some people do is they rub it off using polishing compound. But if you rub it off, you're losing silver metal. And so the weight of your thing is going to be lower than when you start. And so what a lot of people do is they try to reconvert the tarnish back into silver metal by using aluminum. And so they have this was a Chem 1A homework problem also. But they use aluminum plate and then they throw in some salt in there and then they try to reverse this reaction by getting the silver ions and tarnish to oxidize aluminum metal to revert back to silver metal. And this way they don't lose any silver by polishing their silverware. So what that's going to do is it's going to remove silver ions from this and shift it to the right. This is dissolution. Uh-huh.
Did you try it in the airport?
Yeah, I tried it and it works, but it works kind of slowly. It's not so fast. I got to figure out how to speed it up. It's too slow. It's too slow compared to something like hydrogen gas. I've done reduction of metals using hydrogen gas too. That happens very fast.
Would you like cause a reaction that produces hydrogen gas and then bubble it into water?
Yeah, I caused a reaction and then I didn't bubble it into water. I put it into a tube, and this tube was heated, and the hydrogen passed by the metal, and then reduced it. It was pretty immediate, but it's very dangerous because if the hydrogen explodes, then it's big trouble. So I only did it a couple of times, and then I needed like more safety equipment, like explosion shield and some other stuff would be good.
I'm sure there's like chemicals that remove tarnish you could just use if they're safe.
Yeah, there are. This is the low budget homemade type thing.
You did this at home?
The copper I did in the lab, yeah, but the silver tarnish I did at home. I just have some aluminum and was just trying to get rid of the black tarnish on the silver. That's all. So that's an example of redox. What else could we try? Give me one more type of reaction we might try. So any reducing agent stronger than silver metal will work. We'll talk about that later. What's another type of reaction we might try? Acid base. But when you look at silver ions, is silver a Bronsted acid or a Bronsted base? It's an acid? A Bronsted acid has to have an H. Does silver have an H to donate, a hydrogen atom? No. And so this is going to be an example of a Lewis acid-base reaction. And so what we want is silver ions will be the Lewis acid. Give me a Lewis base. In other words, give me a ligand, a good ligand for reacting with silver. I'll tell you an excellent one. An excellent one would be cyanide. Cyanide's great. Cyanide is what we call a carbon or nitrogen donor. It's a carbon donor. When you look at the Lewis structure.
I mean, is it because carbon is more willing to give up its electrons than nitrogen? Or?
No. It's because carbon is very unusual in cyanide. What's unusual about carbon in cyanide?
It's like triple bonded or something, right?
It's triple bonded, but what's unusual about it is its formal charge. What is the formal charge on carbon? In other words, where does this negative charge belong? Does the negative charge belong to nitrogen or does the negative charge belong to carbon? The way I have it written here, it looks as if the nitrogen gets that negative charge, but that's wrong. You know who gets the negative charge? Carbon.
Well, I mean, that kind of makes sense since nitrogen would have all three of its potential electrons shared, while carbon would be missing one. So
Yeah.
it only has 3 bonds.
It only has 3 bonds, so in order to make an octet, it has to gain an extra electron, and it gives it a negative charge here. And so we have 3 bonds in 1 lone pair. And what we would form from this is this. We'd form, how many cyanides attached to silver? 1? No. Not 1. 4? No. 2 or 4? 2. How do you know 2 form? Well, you look it up in a table. This is just observational data. And we'd form this species. This species is very stable. What's the name for this?
Dicyanide, something like that.
Yeah, dicyan. Well, there are two ways you can name it. You can call it dicyano or dicyanide. Either one. Dicyano or dicyanido. Argentate. And the charge on argentate? 1. So this is dicyano argentate 1. But cyanide, like dimethyl mercury, I don't want to work with it. And so this stuff is too toxic. This is my skull and crossbones here. It's too toxic. Give me another Lewis base that's a lot less toxic. It doesn't have to be as good. This is really good. It doesn't have to be as good as cyanide. Just good enough. Hydroxide would be metathesis. We'd form silver hydroxide, and then that would undergo a Lewis to form silver oxide water. So if we add hydroxide, it would be competing like bromide does. Ethylene diamine would be excellent. Or ethylene diamine's too much to write. What's a simpler nitrogen donor? Ammonia. And so let's go with ammonia. How many ammonia is attached to it? 2. How do I know? I looked it up, and sometimes they want you to memorize the pattern, but you know. So we get 2 of these. What's the total charge on this? +1 or +2? +1, yeah. And what do we name this? Diamine silver 1 is correct. Yeah. Ammonias are neutral. Silver's +1. So this is the diamine silver. So what we do is we capture the silver using ammonias. And when you do that, you're going to reduce what we call the free silver. The free silver ion concentration goes down, and we end up complexing it. It's not chelating. Ethylene diamine would be even better. And so if you said ethylene diamine, that's much better. But ammonia is easy because we have ammonia here in the lab. We have lots of ammonia in the lab. We don't have a lot of ethylene diamine in the lab. It's a lot more expensive.
So question, as you're taking the free silver out, I'm assuming the solid, insoluble silver chloride is still having that back and forth and re-adding silver ions, or does it stay?
You know, it's going to re-add them. And so as we remove the silver, then what's going to happen is the reason the reverse reaction occurs is because of a collision between silver and chloride. That collision will result in a precipitate. If you remove the silver, there's no collisions. And so what's going to happen is the reverse is going to stop. And we only have the forward. And so what we end up with is net dissolution. We get forward reaction occur. And what that's going to result in is it's going to dissolve all your precipitate. And so if I have some solid sodium silver chloride, probably the easiest way for me to dissolve the precipitate is by complexing it using ammonia. That'd be the cleanest way of doing it. If I use a reducing agent like aluminum, then I got chunks of aluminum in there, and does it all react or not all react? No, whatever. Or if I use bromide, then I got a mix of precipitates for a while until all the silver chloride is replaced by silver bromide. And so this appears the cleanest because this is aqueous here. The diamine silver 1 ion is just in solution. So we can do it this way. So this is one thing we could do. In fact, what I could do is, okay, I think that's going to be the cleanest. We'll just use a Lewis acid-base reaction to do this. Oops. And so what I'm going to do is I'm going to redraw this. So I have my silver chloride here, solid. And this is going to give me silver ions and chloride ions. And then what I'm going to do is I'm going to remove the silver ions using 2 ammonias here for every silver, and that's going to generate this complex here. And then this is going to be like Hess's law. Like Hess's law, what I'm going to do is I'm going to combine these 2 equations. When I combine these 2 equations, I'm going to get silver chloride plus 2 ammonias. This is going to go to the diamine complex and chloride. And so this is going to be the net reaction here of the steps. So all I do is add more ammonia. You know, more ammonia I add, the more concentrated it is, the more silver chloride it should dissolve. I'm just going to shift it to the right. Yes?
I mean, I know we're still a little bit away from when we start lab, but when we write down our data, are you going to want to do or are you going to want us to do it in pen or?
In pen. Observations in pen.
Okay,
Yeah.
all right.
Analysis can be done in pencil. And so if I want to dissolve this, I'll just add more ammonia. It's easy. But what if I want to reverse this? Is there a way to reverse it? You know, there is a way to reverse this. So increase ammonia concentration, it's going to shift it right, dissolution. But what if I want to reprecipitate it? What's going to shift it to the left? Can I remove silver chloride? If I remove silver chloride, does that change the activity or the concentration of silver chloride? By removing pure solid silver chloride? No, it does nothing. I have to remove the ammonia. And so what are the ways of removing ammonia? One of the ways of removing ammonia is just heat it. If you heat it, you know, ammonia is a gas, you're going to just degas the solution. It's like if you heat a pond of full of fish, as you heat it, it's going to drive off the oxygen, the dissolved oxygen, and eventually the fish are going to suffocate in the pond. Yeah, or they could die from the heat. That's right. So heating it's one way to remove ammonia. And so if we want to shift this, but tell me some chemical properties of ammonia. That's a physical property of ammonia. I want some chemical. Tell me how I can remove ammonia chemically. So I need to know some chemical properties of ammonia. Tell me some chemical properties of ammonia. It's a base. Is it a strong base or a weak base? Weak. And so I want to shift it left. So one way of removing ammonia is by reacting with weak bases. Do what in water? Weak bases hydrolyze water to form what? A little bit of ammonium and hydroxide. Okay, and then what I'm going to do is I'm going to add insoluble cation here. What are my insoluble hydroxides? My insoluble hydroxides are, all hydroxides are insoluble except for group 1, ammonium, calcium, strontium, and barium. So what I could do is I could add like magnesium or iron or lead to this. Lead hydroxide is very insoluble, but I'll just add magnesium hydroxide to this, and I'm going to precipitate out magnesium hydroxide. So this is one way of doing it. One way of doing it is I can let the ammonia, what's this ammonia plus water, what's that called? Ionization, or what is that called? Ammonia plus water is called hydrolysis. And so what I'm going to do is I'm going to let the ammonia hydrolyze water. In the hydrolysis process, it forms a little bit of hydroxide. The little bit of hydroxide I'm going to attack with magnesium. This reaction here is called what? Hydroxide plus magnesium is called a what type of reaction? metathesis. So I'm going to let my Bronsted acid base followed by metathesis, and as I precipitate out magnesium hydroxide as a solid PPT, it's going to shift this reaction to the right, which is going to consume my ammonia, which is going to shift this one to the left. Does that look good? Yeah, it looks okay, but it's not so clean, is it? In fact, and so this would be like acid base followed by metathesis plus metathesis. What would be better? What would be better would just be reacting with acid. And so if I have ammonia here and I take any acid, H+, what am I going to form? I'm going to form ammonium. And ammonium is not the same as ammonia, so probably the cleanest way is just to add acid here, H+, we form ammonium. And what that's going to do is it's going to eat up all my ammonia and shift this to the left, resulting in more precipitate. And so this is probably the cleanest. Probably the dirtiest way of removing ammonia is via redox. Ammonia, what is ammonia in terms of redox chemistry? Is ammonia a electron rich, electron poor, or kind of neither? Rich or poor, nor poor? Well, let me do one more thing. I didn't do Lewis. Before I go to redox, sorry. A Lewis acid base would be adding a better cation. So rather than silver ions, we have versus another cation. What would be a better Lewis acid? Silver is our Lewis acid here. What would be a better Lewis acid? Do you know? Yeah, if we knew the theory quite well, and we could solve it easily, then we could do that here, but we just look up. Is there something that likes ammonia, amine, more than silver ions do? And we would go to, let's see, not here. I don't have my book open, so let me do this. So we're kind of just at the observation phase of things. And so we'd look for things that would favor reacting with amine more. So we use numbers like this. How much does silver like ammonia to form diamine silver 1? We look at the KF, and the KF says this favors product by a huge margin, 10 to the 7th. But when we look at cyanide, cyanide's much better for silver. That favors product in the ratio of 10 to the 21. But what we're looking at is we're looking at competition for the ammonias. So if we try copper, let's see how well copper does. If we put in copper in there and we form tetraamine copper 2 ion, that's 10 to the 12 here. And we compare that to silver. Silver is 10 to the 7, so that's 5 orders of magnitude stronger. Do you see that? Sort of. It's not exactly because it's not linear. So copper 2 might be good. And so we could try it and see what happens. So we go back over here, look up, and we go maybe copper 2. And copper 2 likes amine more than silver ions like amine. Or amine likes copper 2 more than it likes silver ion. And so we set up a competition that way. All right, then in terms of redox, what do we have? How can we remove ammonia in terms of redox? Well, the first thing is, what are the redox properties for ammonia? It's a reducer. Is it rich? Is it a rich reducer? That is, it's a fairly decent reducer, or a poor reducer? That is not a very good reducer. And so what's the first thing you look at if it's not on the chart? Ammonia is not on the chart, so we have to dig deeper. We're going to first calculate the oxidation states. So hydrogen goes first at +1. That means nitrogen is -3. What's the range for nitrogen? -3 to +5. This is rich. It's quite rich. And, well, we could use an oxidizer like oxygen. You know? So, for example, if we had ammonia gas, if we have ammonia gas and we burn it, do you know what we form? If we had ammonia gas and we burn it, we form NOx plus H2O. What is NOx? These are called oxides of nitrogen. And have you ever, you have a car? If you have a car, they measure your NOx emissions. They measure your NOx emissions because NOx are very bad for your health. And NOx are smog, basically. This is a component of smog. And so it's bad for the air quality, too. And so we don't, do you want to do this? Do you want to burn it? And not only that, the ammonia is in water. And so first we have to drive off the ammonia as a gas. So maybe we heat it, and then we try to burn it to convert it into NOx. But then you don't want to breathe it because it's poisonous. So we'll probably do it in the hood. Is that going to be an easy way to do it? No. And so I'm not going to do it this way. And plus, you know, this works. This would be pretty effective if we're ammonia gas. But what if we have ammonia aqueous? Uh-huh.
Is NOx the same as nitrosyl, or is that?
No, different. NOx, you know what NOx are? NOx are NO, N2O, NO2. Just different nitrogen and oxygen in different ratios. X is equal to 1.5. You know, this is X is equals 1. This is X is equal to 0.5. This is X is equal to 2. We just get different ratios depending on what X is. And so X is a variable. Nitrosyls. Nitrosyl is this as a ligand. That's nitrosyl. In fact, this is what happens. I've spilled lots of silver nitrate on my hands. I've also spilled lots of nitric acid. The nitric acid is also a good oxidizer. It oxidizes your skin, your flesh, and produces NO. The NO attaches to some, I forgot what, in your skin and makes a yellow complex. And so if you want black and yellow stains on your hands, then spill silver nitrate and nitric acid on your hands, and you get black and yellow stains. Okay, give me another oxidizer. me another oxidizer to oxidize ammonia. Fluorine? Yeah. But fluorine is very dangerous oxidizer. I was working with fluorine too, and when I started working with fluorine, I was taught the fluorine chemist handshake. Have you ever seen the fluorine chemist handshake? This is how the story goes. The first year you go to the fluorine chemist conference, you go, hey, how's it going? How you doing? Right? And the next year you come back, hey, how's it going? Next year you come back, how's it going? And then so on, and then pretty soon you're just left with a stub. Yeah, fluorine is like lithium. Fluorine is very violent. You want to avoid it if possible. So we are not going to use fluorine. It's way too violent. Give me something else. And fluorine would make nitrogen trifluoride as the primary product, not NOx, which is fine. Sulfur is not the greatest oxidizer. Sulfur is mostly thought of as a reducer. It's easier to burn sulfur than to burn things with it. Sulfur can go either way, though. It's not like oxygen. Oxygen is a great oxidizer. Sulfur is much weaker. If you want to think of it in terms of Coulomb's law, sulfur is a bigger atom, so it's harder to attract electrons to it than a smaller atom. Well, maybe not fluorine. Maybe something like bromine or iodine. Iodine is a lot bigger, less reactive. Fluorine is very small, highly reactive. And so we could try something like that. And so we could get something to oxidize the ammonia. But the problem is a lot of these products are not very clean, and a lot of them are toxic. And so this is not the cleanest way. The cleanest way is just to make ammonium. And ammonium, they use that like in smelling salts and other stuff. So it's not terribly toxic. And so redox, we have a lot of choices here. We could do, metathesis, redox, acid base. So we want to actually have as many options available as possible. All right, any questions on this? So all we're going to do here is we're going to manipulate reactions. We're going to manipulate reactions by forcing it to go forward or forcing it to go backwards by using different techniques. One of the techniques might be temperature, but you got to recall temperature changes the K value, in addition, or it might be chemical or it might be physical, just dilution, or chemical by reacting the species in there. All right, any questions on that? All right, you can work in groups of 2 or 3 if there's an odd person, but not more than 3. So if you have a group of 4, I'll split you up. And that's it from me talking. But if you're okay, if any questions, you can ask me anytime. So I'll stop here. Go ahead and get started.